Okay, let's go for the next topic, which is reflection of light. Imagine that we have a source of light and we have light in this way, right? Spherical waves, correct? Like in this situation, we call this the wave front, right? And also we can represent these waves like waves, right? That, or we can represent these waves, right, like a straight lines. We call these rays, right? The rays, right, are perpendicular to the wavefront. Imagine that the waves propagate, but if the distance increases, right, the waves becomes parallel in this way. Now, if we use the concept of rays, right, the rays are going to be, remember, perpendicular. Now, they take a very nice form, right? The rays are parallel when the source is far away from the observer, right here, correct? So, this is, again, wavefront, right? The wavefront are perpendicular to the rays. Okay, let's take this concept again, that the rays are gonna be parallel. Means that the source is far away. Okay, now, let's go to reflection, correct? When we're dealing with reflection, we have two main types of reflection. We have the specular reflection and we have the diffuse reflection. Okay, types of reflection. We have two types, correct? We have specular and we have diffuse reflection. For specular reflection, the surface of reflection is very smooth compared to the wavelength. Imagine this is the surface is very smooth, right? Smooth surface, right? And we have rays coming, right? And they are reflected, right, very nicely, like in this picture, right? This is the case for a specular reflection. What about diffuse? In this case, the surface is irregular. We have an irregular surface. Imagine like that. Okay, it's gonna be irregular surface, right? Perfect. So we have rays parallel again as before, right, like that. So it's gonna reflect it in this way, this in this way, right, and that one in that way. You see it? So this is a irregular surface, right? So we have diffuse reflection, a smooth surface. We have a very nice reflection. In this chapter, we are dealing with these situations, right, where the surface is very smooth and we have very nice rays. Okay, perfect. Let's start with the first case. The first case is the plane mirror. Okay, when we have a plane mirror, imagine, right, this is the plane mirror right here, and we have an object, any object, let's say right here, this is the object. Of course, this is the plane mirror. Of course, we have the image right here, correct? The image. Now, let's see how this image looks like for an observer. Let's say right here, we have an observer right here. Imagine. So the observer is looking to the mirror, right? Looking to the mirror, and the observer sees, right, light coming from this base, correct? And also light coming from the top, like that. But the light is actually coming from the object, correct? The object, light's coming from the object is the source in this case, correct? And goes to the observer right here. But the image is seen behind the mirror, correct? Also, we can label this as height of the object, right? And height of the image. Also, we can label this distance, the distance mirror to object, the O, and this distance, the I, right? The distance from the mirror to the image. Okay, now when we're dealing with plane mirrors, we have some conclusions. We know that HO must be equals to HI, right? The heights are the same, right? Also, DO is equals to DI. But what happens to the image? When we're dealing with images, we have two types of images. Virtual image and we have real image. The virtual image is the image that is not formed by real light, right? Like in this case, real light is coming from the source, which is the object. So the object is reflecting light, right? Or could be a lamp, right? Creating light, right? So we have light is coming, is reflected by the mirror and goes to the observer right here. But the observer sees the image behind the mirror. But no light is going behind the mirror to form the image. So this image is virtual. Because no real light is forming that image. Another way how we can differentiate, right, between real and virtual images is if we can, right, see the image on a screen, the image is real. Now let's see, you can do it. Let's go behind the mirror, place a screen, and let's try to see the image. Can we see it? No, we cannot see it on the screen, correct? So the image then is virtual image. Now, when do we have a real image? A real image is image that is formed by real light, correct? And also we can see it, right, on a screen. If we have a screen right here, right, and we can see the image, we say that that image is real. Later we have cases in this video regarding to real images. Okay, for the moment we have that the image created by a plane mirror, actually by any mirror, right, is gonna be not by any mirror actually, but plane mirror, right, is gonna be a virtual image. As long as the image is behind the mirror, right, the image is virtual. If the image is in front of the mirror, right, the image is real, correct? Okay, now let's work with those cases later, correct? For the moment, we have this plane mirror conclusions. Height of the object equals to height of the image. Distance object mirror equals to distance image mirror, correct? Okay, perfect. Now let's go to spherical mirrors. This is plane mirrors. Let's go to spherical mirrors. Yes. When we're dealing with spherical mirrors, right? Spherical mirrors, right? We create a shape, right, of a mirror. We know we have the center, where we have the radius R. Now let's cut this sphere, and now we create this mirror, right? A spherical mirror in this way. You see it? It's part of this spherical mirror, correct? Okay, spherical surface. If the reflecting surface is this surface, we call this convex mirror. If the reflecting surface is the internal surface, we call this concave mirror, correct? Now we call this the center. We label one point right here is called a focal point. We can label this as B, the vertex, and also we can have, right, these 2 points A and B. So it's gonna be again the spherical mirror, where again R is the radius of curvature, C is the center curvature, center of curvature. F is called the focal point. We have V is the vertex. We have A B section is called the aperture, and we have a CB section as the principal axis, right? Principal axis. So these are the main points when we're describing a spherical mirror, correct? Perfect. Now let's see what happens when we have the spherical mirrors and we're dealing with reflection. Let's do it. Imagine that we have this concave, right? Concave mirror. Okay, and we have the principal axis in this way, and also we have light coming from a faraway object or source, correct? Imagine we can create, right, this is the sphere, imagine this is the focal point, right? And we have the object which is far away. Of course, remember from the previous analysis that the rays are parallel. When the source is far away, right, the rays are parallel, correct? Now, it's found that for the spherical mirrors, right, these rays are reflected and, right, passes through one point, right? That point is called the focal point, right? So we have rays coming, right, from the source, are reflected, right, and passes through this focal point, correct? Of course, that happens when this area, right, is close to the principal axis, correct? Okay, perfect. Now this is the point where we have the image, right? The image of the object which is far away is formed at that point. Any image, right, using mirrors of lenses is formed where all the rays meet, all the rays converge, right? Like in this case, we have the rays are coming or reflected and they meet or converge at this point. That's the point for the image. Could be real or could be virtual. Okay, perfect. Also the distance from this focal point to the vertex is called the focal length, F, right? F is called the focal length. The distance from the focal point to the vertex of the mirror. This quantity is very, very important in dealing with mirrors or lenses. The focal length. The focal length is very, very important. Correct? Okay, perfect. One more time, we have the image, right, created by a concave mirror, and the image when the object is far away is exactly at the focal point. This is one way how we can find the focal point. Imagine that we have a mirror like this one or a lens. How we can find the focal point? Well, we take a very far away object, right, and look for the image, the best image possible. Now the distance from that image to the lens or to the mirror is gonna be the focal length. Okay, perfect. Now, what happens when we have a convex mirror? Let's do it. For a convex mirror, correct, we have this situation. We have the focal point, imagine it's right there, focal point. Well, imagine that we don't know the focal point yet, correct? But we know that the rays are parallel to the principal axis because the object or source is far away, correct? It's found the same thing as right here, that rays are reflected, correct? But it looks like they're coming, the reflection is coming from the focal, for one point, right? Which is gonna be, again, the focal point as before, correct? So this is for convex convex mirror. Also, we can call this a diverging, right, mirror, and we can call this a converging mirror, right? Converging mirror, correct? Well, the same thing as before. We have the points where all of these rays looks or seems to converge, right, behind the mirror, right? And this is the point again where we have the image. But now how this image is virtual. Why? Because again, light is coming, it's reflected. It doesn't go, light doesn't go behind the mirror to form the image, correct? So this image is virtual. What about this image? This image is real. Why? Because light is coming, real light, rays are coming and reflected and passes through this point. Another ray is coming, reflected and passes through that point, right? So real light is forming this image. So we can see the image on the screen. We have a screen right here. We can see that image. So the image is real. What about right here? Can we see the image behind the mirror? No, right? The image is virtual. Perfect. Now, let's use these ideas to form images. Okay, how an image is formed using this concept. Let's do it. Imagine that we have a concave mirror, right? Like this. Perfect. We have the principal axis. Imagine that this is the focal point. Okay, we know how we can find it. Okay, perfect. Now we have an object right here, object, and we use the technique that is found right when we work to find right the focal point. Remember how the focal point is found? Well, we have a faraway object, correct? Faraway object. So light is reflected, correct, and passes through one point. That's the point for the image, the focal point, correct? So this is a technique that is used for finding images. So we have a ray that is parallel, right? When the ray is parallel to the principal axis, what happens? It's reflected and passes through the focal point. So it's reflected and passes through the focal point, correct? Also, we can go backward. If we have a ray, right, that passes through the focal point, is reflected parallel to the principal axis, right? If we have a ray that passes through the focal point, is reflected parallel to the principal axis, correct? Like in this way. Also, we have another ray that when that ray is touching the vertex, right, or directed toward the vertex, that is reflected with the same angle. So these two angles are the same, right? We have these three main rays that help us to form an image, right? We have that ray, we have the second one, and we have, let's say, the third one. And what is the image? Again, the image is at the point where all the rays meet. Could be real image or could be virtual image. In this case, real light is coming and forming the image, and this is a real image. Correct? Perfect. Now let's use the same technique for another case. Look, this is a convention when we're dealing with mirrors and lenses. We place the object to the left of the mirror, right? That's the convention when we start the analysis. Like in this case, the object is at the left of the mirror. Imagine we have another case, again, using concave or convergent mirrors, correct? Imagine this is the principal axis, one more time. This is the focal point. And let's see what happens when the object is right in between the focal points and the vertex. How we can find the image? Okay, let's do it. Let's use the same technique as before. If we have a ray that is parallel to the principal axis is reflected toward the focal point, correct? And we have a ray that's coming right from the focal point, right, is reflected parallel to the principal axis, correct? But look, in this direction, these rays diverge. But if we are going backward, they looks like they meet behind the mirror. So let's see again, where is the point where all these rays meet? And it looks like they meet, this ray meets behind the mirror. If the image is behind the mirror, the image is virtual. So in this case, we have a virtual image. Virtual right image is behind the mirror. We cannot see it on the screen, correct? And look, also when the image is virtual, right, this is the object, right, the image is upright. If the image is upright, the image is virtual. If the image is upside down, the image is real. Okay, perfect. Great. This is the case when we have concave mirrors. What about convex? Let's go to convex mirrors, right? The same thing. We have the principal axis. Imagine the focal points right here. We use the same technique. We have a ray parallel to the principal axis, how is reflected toward the focal point, right? This is the focal point. But right here, the focal point is behind, right? So it looks like actually it's coming from the focal point in that way. Imagine it goes in that way, correct? Perfect, like that. Now let's go to the next ray. This one, the ray that goes toward or passes the focal point is reflected parallel to the principal axis. Okay, let's do it. So we have a ray that goes right to the focal point is reflected parallel. Correct? Great. Now, one more time, in this direction, these rays diverge. But what happens if we're going right backward? Well, this ray is coming, looks like it's coming from this point, and this ray is coming from that point, right? Or from that direction. Now, what is the point where these rays meet? Right here, right? They meet at that point. Look, the points where all the rays meet or looks to meet is the point for the image, right? So this is the image again. The image is formed at that point, at that position, at that distance. But again, it's behind the mirror and it's upright, so it's gonna be virtual image. So we have the way again how an image is formed, right? Using spherical mirrors, right? Using these three rays. Great. Now let's find an equation. Let's find an equation that helps us to work with distances, right? The distance of the object to the mirror, the distance from the image to the mirror, right, in the focal length. We have an equation, and that equation is called the equation of the mirrors. Correct? Okay. Let's do it. Let's go for the mirror equation. Okay, the mirror equation. The mirror equation. Let's do it. Let's do it. One more time. Imagine that we have this concave mirror, correct? We have the principal axis, and let's say this is the focal point, and we have the object right here. As we did before, remember, let's find that image, right? Using these techniques, we have this one, and also let's use this one, right? Toward the vertex, right? So we have the images formed right here, correct? So this is the focal point, imagine, and this is the object, and this is the image. How is this image? Real, right? It's upside down, right? A real light, right, is coming, reflected, and passes to this point where the image is. So the image is real. Actually, the passes and from that image right there. Great. Now let's label these distances. The distance from the focal points to the vertex is called f, the focal length. The distance from the image to the vertex of the mirror is called distance di, right? And from the object to the mirror is called, right, do. One more time, this is focal length, the distance from the focal points to the vertex of the mirror, right? Di is the distance from the image position to the vertex of the mirror, and do is the distance from the object to the vertex of the mirror. Correct? Okay, now let's try, we have another one, right? Another ray, which is this one. Imagine that they meet right here. Okay, imagine they meet right there. So these are the three rays that help us to form or to find the image. Now let's use these rays to create the formula. Okay, let's create the formula. Yes. Okay, almost done, almost done. Okay, so we have, let's say, the focal points right here. We have the object, correct? And let's go to this ray, right? This one and this one, correct? Perfect. Now imagine that that's the image right here, right? This is the image right here. But we can send the image right here for the moment to create a right triangle. And also remember, this is labeled O and this is HI, right? As you can see, they have the same angle. So these two are similar triangles. And what happens when we have similar triangles? Like in this case, look, these two are similar triangles, correct? In this angle theta, they have the same angle, like in this case, correct? If I label this A and this is B, and this distance A and this distance B, now we use tangent, okay? Tangent theta is equals to opposite over adjacent, right? B over A, or, right, big B over big A, correct? So we use this condition for similar triangles. The same thing happens right here. Now, what should be this distance? This is F, right? This distance, what about this distance? This distance is this minus this, correct? So this distance from here to here is just dO, right, minus F, correct? And now let's apply the condition for similar triangles. Great. So we have that HO over adjacent, which is dO minus F, it must be equals to HI, right, over this distance, which is F. Similar to this situation, right? General case, similar triangles. Now let's arrange it, right? We have HO over HI must be equals to dO minus F over F, right? This is a convention that we use right here because HI is, the image is upside down, we take this as negative. Okay, let's take it as negative. Perfect. Now we create the first conditions for these two triangles. Let's go to another set of triangles, right? Now let's take this set to the vertex. Okay, let's do it. Again, we have the same situation, the same mirror, same object, right? This is the focal point. We have the object right here. Now let's use these two similar triangles, right? These two are the same angle. Imagine that the image is right here. Perfect. This is the object, HO, and this is the image, HI. Great. And one more time, let's use the condition for similar triangles. It's gonna be HO, right, over this distance, which is dO, must be equals to HI, right, over this distance, which is di, correct? Now let's rearrange it again, and we have that HO over HI equals to dO over di. Again, this is the convention that if the image is upside down, that HI is negative. Okay, HI is negative. Now these two are the same. Look, these two quantities are the same, so means that these two equations are the same too. So we have that dO over dI must be equals to dO minus F over F. And what is this? This is a dO over F minus 1, correct? Now let's divide, this is gonna be like this, okay? Now let's divide everything by dO. What happens when we divide all of this by dO? What do we have? 1 over dI is equals to 1 over F minus 1 over dO. Correct? Perfect. Now we arrange this equation in the traditional way that we have. It says 1 over dO plus 1 over dI equals to 1 over F. This is the traditional form for the equation of the mirrors. And this is the mirror equation, right? The mirror equation. Okay, so this is again the equation that is used for mirrors. It's also used for lenses in the next topic, which is lenses. We're gonna get the same, we're gonna find the same formula. Okay, now let's go to the sign convention, correct? What happens when a quantity is real and when it's virtual? Depends on the sign, or it's related to the sign. Okay, let's do it. Let's find this convention. Let's use this convention, right, that is used for the mirrors. The same thing for lenses, about the same thing for lenses. Great, let's do it. So we have, for example, that F, right, F is positive, right, for concave mirrors, right, and negative for convex mirrors. So if we have a problem, right, where it says the focal length is negative, means what? The mirror is a convex mirror. Or if the mirror is convex, the focal length must be negative. Okay, great. What about DO? DO is positive, right, for real object, and negative, right, and negative for virtual, right, for virtual object, for virtual object. What about DI? DI is positive, right, the distance positive, right,